This is Algebra Lesson 8-5, Division Powers of Exponents. You can use repeated multiplication to simplify fractions. If you expand the numerator and the denominator, if it's using repeated multiplication, you can then cancel like terms. For example, if I was going to work with this particular problem here, I have 3 to the 8th is 3 times 3 times 3 times 3 times 3 times 3 times 3. I believe that's 8. 3, 6, nope. Times 3, that's 8. All over 3 times 3 times 3. Which means I can now cancel anything that's common. This 3 can cancel with that 3, this 3 can cancel with this 3, this 3 can cancel with that 3, and I'm left with 3 to the 5th power. If you look at this, hopefully you'll notice that 3 to the 8 minus 3 is equal to 3 to the 5th power. Which in other words means if we have a division of exponents, we can subtract the exponents to get to our final answer. This illustrates the last property of exponents that we're going to talk about in this chapter. And that's the property of exponents of dividing powers with the same base. For every non-zero number a in integers m and n, if we have a to the m divided by a to the n, we will come up with a to the m minus n. In other words, you subtract the exponents, just like I did in the previous example. So, let's look at some examples to see if we can simplify these. I'm going to simplify b to the 4th divided by b to the 9th. First thing I'm going to do, I'm going to just simply look at it and go, okay, b to the 4th divided by b to the 9th is same base, so it's going to be b to the 4 minus 9, which is going to become b to the negative 5th power, but I cannot leave it as a negative exponent, so that becomes 1 over b to the 5th power. And we're done. Problem number 2, a to the 2nd times b divided by a to the 4th b to the 3rd. That becomes a to the 2 minus 4, b to the 1 minus 3, because remember if an exponent doesn't, if a variable or a number does not have an exponent, that exponent is always a 1. So this becomes a to the negative 2nd, b to the negative 2nd, which simplifies to 1 over a squared b squared. Number 3, lots of variables here, x's and y's and z's. So we have x to the 2 minus 1, y to the negative 1 minus 4, make sure you pay attention to negative signs, z to the 4 minus a minus 3, again, pay attention to negative signs. This could be a really bad thing if you mess up some negative signs. You're going to end up having negative exponents where you should have positive exponents, or positive exponents where you should have negative exponents. So this problem becomes x to the 1st, y to the negative 5th, z to the 7th. X to the 1st, y to the negative 5th, z to the 7th. The x and the z are positive, so they can stay in the numerator. The y to the negative 5th needs to move to the denominator. So this will become x, z to the 7th, all over y to the positive 5th. Because remember, when you move something from the numerator to the denominator, the exponent becomes positive. So there you go. X, z to the 7th, all over y to the 5th. When you divide numbers that are in scientific notation, you can use the properties of dividing powers with the same base. In real-world situations, decide whether to write the result in standard form or scientific notation if not told to do one or the other. Okay, for example, a small dog's heart beats about 64 million beats in a year. If there are about 530,000 minutes in a year, what is the dog's average heart rate in beats per minute? Okay, well, 64 million. Let's start with that. 64 million. I'm going to transfer that to scientific notation. And remember, millions is to the 6th decimal place. So 64 million would be 64 followed by 6 zeros. 1, 2, 3, 4, 5, 6. So in scientific notation, that would be 6.4 times 10 to the 7th power. So I have to move the decimal point 7 places to the left. And it says if there are about 530,000 minutes in a year, let's change that to scientific notation. 530,000. Which would be 530,000, which which converts to 5.3 times 10 to the 5th power. Now it says, if there are that, just think of this, 6.4 times 10 to the 7th beats in 1 year. And we need to figure out the average heart rate in beats per minute. So 6.4 times 10 to the 7th beats in 1 year. And there are 530,000 minutes in 1 year. Okay, so that means in 1 year, there are 5.3 times 10 to the 5th minutes. Okay, so my years cancel out here. So this gives me beats per minute if I divide it out. So I simply need to divide it out. So I'm going to take 6.4 times 10 to the 7th, and I'm going to divide that by 5.3 times 10 to the 5th, which simply means separate it and divide it. So that's going to be 6.4 divided by 5.3 and 10 to the 7th divided by 10 to the 5th. Okay, these will be multiplied. If I take my calculator and I take 6.4 and divide it by 5.3, I'm going to get a very long decimal number, so I'm going to round it. So that's going to be approximately 1.21 to the nearest hundredth times 10 to the 7 minus 5 is 10 to the 2nd. I normally wouldn't answer a real-world problem in a scientific notation when it can be written fairly simply in standard form. So 1.21 times 10 to the 2nd in standard form is 121. So 121 beats per minute. So a small dog's heart beats approximately 121 beats per minute, which is a fairly rapid heartbeat considering humans that are fairly sedentary, not working out or walking hard or anything like that, have an average resting heart rate around 70. When they first get up in the morning, it should be even lower than that. All right, let's take a look at some next things. Now, we can also use repeated multiplication to simplify the expression xy quantity to the 3rd power. Remember, when we took a quantity to a power, we distributed that power to everything inside of the parenthesis. We're going to essentially do something similar here, because if I look at this, I have x, y, quantity to the 3rd, which means x times x times x over y times y times y, or in other words, x to the 3rd over y to the 3rd. Just like before, when we took a quantity to a power, we distributed the exponent throughout the entire quantity. We do the same thing with a quotient. You still distribute that exponent throughout the entire quotient, leading us to another property of exponents, raising a quotient to a power. For every non-zero number a and b and integer n, a, b to the nth power becomes a to the n over b to the n. Okay. Let's go through some examples here. We're going to simplify 3 divided by x squared all to the 2nd power. That becomes 3 to the 2nd over x to the 2 times 2, because we're going to distribute the 2 here. We're going to distribute 2 down here. 3 squared is 9. X to the 2 times 2 is x to the 4th, so we get 9 over x to the 4th. Cannot simplify it any further, and we're done at that point. If we have x divided by y squared all to the 3rd power, again, distribute that exponent to the numerator, so that becomes x to the 3 times 1 over x to the 3rd, and y to the 2 times 3 or y to the 6th. So we get x to the 3rd, y to the 6th, divided by y to the 6th, excuse me. T to the 7th divided by 2 to the 3rd, all to the 2nd power. Again, distribute your exponent. So we get t to the 7 times 2 divided by 2 to the 3 times 2, which becomes t to the 14th over 2 to the 6th. 2 to the 6th can be easily multiplied out. 2 to the 6th is 64, so this becomes t to the 14th all over 64. Raising a quotient to a power is the same as raising a power. to a power. Now, let's look at this. This is just a little bit of a difference here. Okay. We can use what we know about exponents to rewrite an expression raised to a negative power to raise it to a positive power. Okay. You're looking at this, and we see a over b to the negative nth power, which becomes, okay, we remember this, it becomes, you can do it a couple of ways here. I'm going to just do it this way. I'm going to take this becomes 1 over ab to the positive nth power, because I'm going to change this to a positive exponent first. From that step, this 1 over that means, this means division, remember? So essentially I have 1 divided by a over b to the nth power. If you remember your fractions, that's 1 over 1 times the reciprocal, which would be b over a to the nth power. 1 times b over a to the nth power becomes b over a to the nth power. Okay. Okay, therefore, essentially, a over b raised to the negative nth power is the same thing as saying b over a to the positive nth power. That's what we're saying that that equals. Which is very handy when you go to simplify things taken to a negative power, like these problems. If I take 3/4 to the negative third power, that's the same thing as saying 4/3 to the positive third power, which is 4 to the third over 3 to the third. 4 to the third is 64. 3 to the third is 27, so this becomes 64/27. Negative 1/2 to the negative fifth power becomes negative 2 over 1 to the positive fifth power, which becomes negative 2 to the fifth over 1 to the fifth. Okay. Negative 2 to the fifth, and by the way, that would be in parentheses. It's taken to an odd number of exponents, so it's going to stay negative. Okay, negative 2 to the fifth is negative 32. 1 to the fifth is just 1, so this just becomes negative 32. 1 is one of those nice numbers. It's 1 to the 8th power is 1, 1 to the 5,712th power is 1, and 1 to the 8th power is still 1, and you're just multiplying it by 1. So 2r over s, quantity to the negative first power, becomes s divided by 2r, all to the positive first power. So this becomes s over 2r, because 2 to the first is 2, r to the first is r, s to the first is s. Last but not least, 7a divided by m all to the negative second power becomes m over 7a quantity to the second power. So that becomes m to the second over 7 to the second, a to the second, which is m to the second over 49a squared. As you can see, our properties of exponents keep building on each other. So it's really helpful that you keep them straight. So you might need to review them once in a while so that you can keep them straight. But they're not difficult to work with.